Welcome to another day of long distance learning from Old Guy Physics. Our new topic for this week, coming back from spring break, is the topic on light. And to try to get you to see some basic ideas about light, one of the very first things that I wanted you to see was, how is light produced? And you've seen some things that you had in a chemistry class last year, and I'm trying to add to it, but at the same time, you know, that there isn't a lot of demonstrations that I can do right now. So see if you can follow along with me and take some good notes and ask some good questions. Okay? First of all, the thing that we should recognize is that there are several places that we see light being produced, but we're really not sure how that light is actually being made. Okay? For example, light is traveling from the sun to the earth, and we see it as rays of light. When they say rays of light, R-A-Y-S, rays of light, all they're referring to is the fact that we see light traveling in straight lines. You often see that when you see light from the sun that's passing by a cloud, and you see the rays of light coming off the cloud as a result of some of the light being blocked by the cloud and other light that is coming right by there, and you see it as strands or straight lines of light. When you look at a laser pointer, you see light that's traveling in a straight line, and we would call that a ray of light. But we also know that light is said to be a form of electromagnetic radiation. Okay, so if we're looking at an electromagnetic wave, one of the things that we should recognize is that there are two parts of that wave that make up that ray. And so if we see the light traveling from the sun to the earth, one portion of that is the electromagnetic part. Okay, so this is if this is a vertical axis, and let me put it in a different color so maybe it'll make it easier to see. And this is the horizontal axis here. Then there is a second part of the wave that is horizontal. So the blue wave that I tried to draw there shows vertical motion, and the horizontal part, which is in purple, represents perhaps the magnetic part of the wave. Now, it's all traveling in a straight line, but electromagnetic radiation actually has an electrical part and a magnetic part. And when we studied magnetism, we learned that magnetism worked at right angles to the flow of electricity. And so we can see that the electromagnetic waves actually, they have two parts, that vertical part and that horizontal part. Now, that's not to say that it only travels in the vertical and horizontal plane, but if we were to look at, if we could look right here, and it's not a great picture of an eyeball, but if we could look right down the ray of light from the point here, looking back at it, then it doesn't necessarily have to be just in the horizontal and vertical plane, but as we're looking at that ray of light, that dot represents the arrow point right here. It could be in this plane of reference, it could be in the horizontal and vertical plane, but it could be in any one of those planes of reference as it's traveling in that straight line. Now, of course, for the longest period of time in the history of man, the number one form of light was the sun, and the sun produces light, which obviously we can see it keeps everything alive here on the earth. A second way that light was produced that man was familiar with was the idea of the flame, the open flame. So a candle was a good example of a way of producing light. And what we found out was that a combination of the wax along with the wick would cause the flame to burn and produce light and heat as well. We also should recognize that the sun produces light, but produces heat as well. Now, in chemistry last year, there was a device called a light generator. And what it was nothing more than a black box that was plugged into the wall, and the teacher took different gas tubes. They took different gas tubes, and when they plugged them into the generator and turned the switch on, then this light tube gave off a tremendous amount of light, which everyone in the classroom could see. And perhaps you wore these special glasses that were called diffraction gratings, and they used those glasses to separate that light into its individual frequencies. And I'm hoping that you will remember having done that in chemistry class. Another example, and I don't know that you can see it, but I'm going to point to it, is that there is light being produced by the fluorescent light fixtures that are on the ceiling here in the classroom. And the electricity again is flowing through the light fixture and through those gas tubes, those fluorescent tubes, and they are producing light to light up the classroom. Now, in all of those circumstances, there is energy being used to produce light here. There is energy in the form of electricity being used to form light here. And there is energy in the form of heat energy that's used to form light here. And so all of those forms of energy are being used to produce light, but it still doesn't explain how light is actually produced. So if you give me a moment, let me erase a little bit of the board here, and let's talk about this diagram specifically, because it helps us to see how the light is produced. Now, in this experiment that you did in chemistry, there was in the gas tube, what the very first gas tube would have been hydrogen. And if we look at a picture of hydrogen, hydrogen has a proton in the center with an electron on the outside. And that would be our electron dot picture, so to speak, for a hydrogen atom. And we know that there are additional energy levels out here that go out farther and farther from the nucleus. It's just that because it only has one electron, that electron is going to be found in the first energy level. And so if we number these 1, 2, 3, 4, 5, 6, and there's a seventh one out here somewhere. I'm not going to draw that. But the electrons are whirling in an electron cloud around the nucleus. And the place where the electron is normally found is called the ground state. The ground state. So if the electron for hydrogen is found in the first energy level, that's its normal place of location. Now, if this hydrogen atom, and you know, when we're talking about an experiment like this, there's billions and millions and millions of those hydrogen atoms. But we're just going to talk about this one. Then we know that this electron is being bombarded with energy. And the energy that it's being bombarded with is electricity, because we've got it plugged in the wall over here. And when we flip the switch on, the electricity passes through the gas tube. And when this electron absorbs energy, then it has the ability to jump to a farther out energy level. Think about what the name of these things are. These are energy levels. So if it absorbed enough energy to go from the first energy level to, say, the fifth energy level, then that is a certain amount of increased energy that the electron has. Now, when it jumps to this spot out here, this is called the excited state. Now, one of the things that we know about the excited state is that, number one, it's temporary. Number two, the electron doesn't stay there for a very long period of time, but is more, to give it a personal quality, it's more comfortable being where it's supposed to be, as opposed to being at that excited state. And so what we find happening is that electron absorbs the energy and jumps to that excited state. It stays there for a brief time, maybe milliseconds, and then it has a choice of dropping down in various jumps till it gets back to its original location, which is its ground state. Well, if it takes energy to get it out here, then when it drops back down towards the ground state, it's going to give off energy. And the energy that it gives off is going to become a photon, or a package of light energy. It's a particle, if you will, of light energy. And because it has a specific energy, it will also have a specific wavelength. And so there were lots and lots of different experiments in chemistry around the turn of the century, 1900s, 1905, 1910s, in that ballpark. And the electrons going to the excited state and dropping back down to its ground state, photons of light were being given off. And one of the things that they found out was that it wasn't random, but that it was specific to the kind of electron that was being excited. And so when you look at a hydrogen gas model, you always got the same basic frequencies or wavelengths of light that were being given off each time. And from that, the scientists deduced that there had to be specific distances from the nucleus that the electrons must be going to. If it goes out to the fifth energy level and it drops back down, it gives off one particular kind of light. When it goes out to the fifth energy level and drops back down to the second, it gives off a different frequency of light. And so those frequencies of light were directly related to the amount of energy from those energy levels for that particular element. Now, when you looked at those things in chemistry, you ended up seeing in the picture, you saw specific lines of light that went along. It looked something like this. It was called an emission spectra. And that showed these specific lines of light that were being emitted. Emission, the word emitted, to be given off. And so these were specific colors. And that goes back to the idea that it was going to give off specific frequencies. It wasn't random. They didn't get one line one time and another line another time. But every time they observed this, they always got the exact same colors in the exact same frequencies. Now, another thing that's kind of interesting is that there were scientists that studied this, and initially the only thing that they could see was that it was giving off light in the visible light range. Later on, as the technology became more sophisticated, they also found out that they gave off specific frequencies of light in the ultraviolet region, and they also gave off specific frequencies of light in the infrared region. And those scientists that got credit for it there was a guy named Balmer who did the visible, there was Lyman who got the ultraviolet, and there was the Passion series. All three of these were the scientists that were given credit for discovering these specific lines of light that went along with these lines of light that you can see here. Now, if this was UV and this was infrared, you could understand that the human eyeball is not capable of seeing these frequencies of light. And so it would be important for them to have other technologies to be able to witness these forms of light being given off, just like Balmer was able to see the visible light. Now, this is the beginning or video number 1 on how light is being produced. And if you have questions, write them down, save them for the first face-to-face meeting that we have, and be ready to look at video number 2. Thanks for watching.